Let us discuss the fundamental theorem of calculus part 2. The fundamental theorem of calculus 2. Fundamental theorem of calculus, include a 2 there. Then it states that if f is continuous on, of course, a closed interval AB, and a capital letter F is any antiderivative of small letter f on AB, then the integral from a to b of f of x dx is equal to the antiderivative evaluated at b minus the evaluated at a. Simply that. So this is going to make our lives very easy, because this is what we were waiting for all along. Example. Let us evaluate. Let me continue with this one. Evaluate the integral from 1, say, to 3 of 4 minus x squared, let us put a square, dx, like that. So we are saying that as a solution, the integral from 1 to 3 of 4 minus x squared dx is equal to, we integrate 4 with respect to x, we get 4x. Then we integrate x squared with respect to x, we get x cubed over 3. Now, it means 4x minus x cubed over 3 is the antiderivative of 4 minus x squared, right? And you may observe that if we start with the limits here, a and b, we don't have our constant c, because now we are talking of a number, an exact number. So we write the antiderivative like this without that number, but we indicate that we are going to evaluate it from 1 to 3. And now this is like f, capital letter F. Then we must find it, or find its value at 3. Capital letter F, we find its value at 1. We subtract the 2, then we get our answer. So what we have here, it's equal to evaluated 3. It means 4 times 3 minus 3 cube over 3, like that, minus this minus sign here. Then we evaluated 1, which is 4 times 1 minus 1 cube over 3, like this. And what do we get? 4 times 3 is 12, minus 27 over 3 is 9, minus 4 times 1 is 4, minus 1 over 3, like that. Then 12 minus 9 is 3. 4 minus 1 over 3 is like 12 minus 1, which is 11 over 3. And then 3 minus 11 over 3 is like 9 minus 11 over 3, which is minus 2 over 3. That's the number we are interested in. Now, if that is the case, then we can move on to do the second example. I hope this one makes sense. Let us take now example number 2, where they say evaluate the integral from minus 2 to 2, but they've given us f of x dx, and they say where f of x is a piecewise defined function, is equal to minus x squared plus 1 if x is less than 0, and it's x cubed plus 1 if x is greater or equal to 0. So the integral from minus 2 to 2 of f of x dx is equal to the integral from minus 2, we rest at 0, of f of x dx, plus the integral, we start from 0, we move to 2, of f of x dx. I hope it makes sense. Now, when we come to the next point, we have the integral from minus 2 to 0. With minus 2 to 0, we are talking of values of x which are less than 0, so we'll have minus x squared plus 1 dx, like that, plus the integral, this is positive, from 0 to 2, and then it's x cubed plus 1 dx, like that. Then we integrate this, will give us minus x cubed over 3 plus x, and then we are going to evaluate it from minus 2 to 0, plus then the very same x the power of 4 over 4 plus x. This will be evaluated from 0 to 2, and then when we substitute 0, this will be 0, that will be 0. So it's kind of with 0, and then minus, and we evaluate it at minus 2. We put minus 2 here, it will be 8 times that, it will be positive 8 over 3. Then we subtract 2, like that. That's the first part. Second part, we have a plus, we put a 2 here, 2 to the power of 4 is 16 divided by 4 is 4. Plus, we put 2 there, then it will be a 2, then we subtract 0, like that. This is going to be 8 minus 6, which is 2 over 3, so it's negative 2 over 3, like that. This will be plus 6. Then when we add this, this is 18 minus 2, which is 16 over 3, or if we want, we can say 5 whole numbers, 1 over 3. That's how we do it. Then the next example will be in line. Let us just show you the technique here. We speak now of definite integrals using substitution. In other words, again, we are talking of the second, the fundamental theorem of calculus part 2, but now we are looking at a situation where we can use the u-substitution. And what is essential here is to note that we should not mix things which are not the same. We should not confuse u with x. Let me put it that way. For example, evaluate the integral from 0 to 2 of x square root of x squared minus 3 dx. So as a solution, again, we will encourage you to follow what we are going to represent here to show you, because if you mix the x and u, it's not very interesting, and you will lose marks by mixing x with u. You will lose marks. So it's better to do it this way. U substitution, you let your u take the inside function, which is x squared minus 3. Fine. Then what do? We differentiate, and then we get du dx, it's equal to 2x this implies that 1 over 2 du is x dx, like that. So we don't want to mix things which are not supposed to be mixed. We mix them, we lose marks. So now we must check our limits. These are values of x here, and we want to rewrite this in terms of u. So it's wrong to say, to have u here and still have 0 and 2 there. It's wrong. It's wrong. So now what we do, we change the limits. Let me write here, change the limits. When we change the limits, we observe that we have a lower limit and an upper limit. 0 is a lower limit, that one is an upper limit. So we may say when x is equal to 0, what about u? We said u equal to x squared minus 3. So x is 0, we put 0 there. It means u will be equal to 0 minus 3, which is minus 3. Then when x is equal to 2, u will be 2 squared minus 3, which is 4 minus 3, which is 1. So now we are sure that if we start off with something in terms of x like this, x squared minus 3 dx, if we want to rewrite this in terms of u, we will write the integral when u is 0. Instead of putting 0, we put minus 3. When x is 2, instead of putting 2, we put 1. And then x dx is 1 over 2 du, 1 over 2 du. What is our u? Our u is x squared plus 3, so we will have u square root like that, and then we have our du. So we didn't mix anything. This is u, this is u, that is u. So if you put 0 here and 2 there, whereas you have u here and u there, you are wrong. So this will be equal to, then we integrate, we have our half, which is there, then we multiply by our 2 over 3, then we multiply by our u, we added 1 there, so it will become 3 over 2, and then this is evaluated from minus 3 to 1. See how easy it is? Because now we no longer would no longer go back to x, we just evaluate it straight away. So we've got our 1 over 3 here, because this and that will cancel, we have 1 over 3, and then u, the first, the upper limit is 1, so square root like that, and then cube is still 1, and then we subtract, and then we put our minus 3, then we raise it to the 3 over 2, like that. And this is 1 over 3 into 1 minus, because this will be squared, and then it will be cube, and then it will be square root of 27, I think. And this is 1 over 3 into 1 minus square root of 27 is 3, square root of 3. This is the number that we are interested in. So the main thing here, I repeat, is that we should never mix u and x. When we talk of u, it's better to change the limits, and then you have that. Else, you can work it out, just like what we did when during our contact lectures, without putting the limits. After finding the function, the antiderivative, you bring in the limits, which are in terms of x, and then you evaluate, but it's a little bit long. In the pamphlet, I also showed you how to do it using x values. So here I just decided to do it this way because this is what I want to emphasize. The second example it's like this. The integral from minus 3 to minus 2 dx over the square root of minus 5 minus x squared minus 6x, like that. We can do this by u-substitution or straight away directly. So, but the point here, the first thing that we observe is that we cannot just say let this be equal to u and then we think we will get the answer we want. So what we do, we observe that we must complete the square. And the method we discussed is we look for a certain number c given by middle term squared, which is minus 6x. You square that, you divide by 4 times the first term, which is minus x squared. Then if you do that, 6 times 6, you divide 3, it will be minus 9, like that. So it tells us that minus 5 minus x squared minus 6x is equal to minus 5 minus x squared minus 6x minus 9 plus 9, like that, which tells us that this and that will be a 4, and then we have a minus, and this side it will be x squared plus 6x plus 9, like that, which is a 4 minus x plus 3 all squared. So this is telling us that what we started off with, minus 3 to minus 2 dx over the square root of 5 minus x squared minus 6x is the same thing as the integral from minus 3 to minus 2 of dx over the square root of 4 minus x plus 3 all squared, like that. Now, if you want, maybe I can do it that way, but it's not really necessary. We can say let u to be equal to x plus 3. So if we do that, du will be equal to dx. And then since we want to write everything in terms of u here, we must change the limits. We observe that when x is equal to minus 3, u will be equal to, we put minus 3, here we get 0. And then when x is equal to, say, minus 2, u will be equal to, put minus 2 here, plus you get a 1. So this will give us the integral. Instead of minus 3, I'm going to put 0. Instead of minus 2, I'm going to put 1. And then instead of dx, I'm going to put du, and over the square root of 4 minus, instead of x plus 3, I'm going to put u and then square, like that. This now reminds us of the arc sign, which is simply, because this is our a is 2 here, so the answer is arc sine of u over 2. And then we're evaluating from 0 to 1, like that, which is now the arc sine of 1 over 2 minus the arc sine of 0. You see how easy it is if you change the limits. And don't forget, we calculate this using radians. If you do it in degrees, you're just wasting your time. So this will be pi over 6. This will be 0, which is simply pi over 6 radians. There we are.